We're now going to look at applications of vectors. We're going to start with the velocity vector. One thing I want to point out to start is that when we speak of velocity, velocity includes a direction as well as a speed, whereas speed is just the speed of the vector. The formula is, if we're looking at a direction vector, we can take the magnitude, the absolute value of the magnitude, and the direction with that x and y component. So in our first example, we start by being given a vector equation, which I reviewed in the last video. And A is asking us to find the object's initial position. So the initial position means that t is equal to 0. So if I take the vector equation, so I have x, y, 7, 5 plus, it would be 0 times the direction vector. So we would be left with a horizontal component of 7 and a vertical component of 5. So therefore, if you remember back to our vector equations, this is a point. So therefore, the object is at 7, 5. So remember, this is your direction vector. And this is your point when we're looking at a vector equation. For B, it's asking us to find the velocity vector. So we're going to use that information that I just showed on the previous slide. So we have 6, -8, which is our direction vector. So that means that the object moves in a horizontal direction of +6 and a vertical direction of -8 every second. That's all it's asking, is to identify the velocity vector, which is really our direction, but put it in terms of time. To find the speed means that we'll take that same vector, we apply our formula, so we get 36 plus 64, which is equal to square root of 100, which is 10, and meters per second, which is given distance of meters, that's given in the question, and seconds is given in the question as well. If the object continues in the same direction but increases its speed to 30 meters per second, state its new velocity vector. So for D, we're saying that we have 10 meters per second and it's increasing to 30. So what's happening is it's being tripled. So we can look at that new velocity vector is going to be 3 times the original one. So it's going to be 18 and -24. The next is constant velocity problems. So this means that we have an object that's moving at a constant velocity, so it's not changing at all. We have where the object is initially starting, and we can write that in an equation form. So really what we're doing is we're just looking at displacement equals time times velocity, which is similar to your distance equals speed times time. We just change the wording when we're talking about vectors. So what we're saying is very similar to our vector equations. We have a point, which is where we're beginning, that's our initial time, and then we have t, some unit of time, times our constant velocity vector. So let's look at an example. An object is initially at 5, 10, so that's a coordinate, and moves with a vector, velocity vector of 3, I minus j. So remember, this would be 3, -1 as our velocity vector. And we can call that b if we want to relate it to the equation above. So our equation, remember, is r is equal to a plus t times b. Well, our a value is going to be where we initially begin, which is 5 and 10, which is given in the question. So if I just create a diagram here we have 5, 10, and that is a. And then we have the velocity vector. So from our point, we're going to move 3, -1. So it's going to look, and this is just a diagram, something like this. So b is equal to 3, -1. So when we're asked the position of the object at any time, so it's just saying come up with an equation. So we have x, y is equal to 5, 10 plus t, 3, -1, and we do have to say that t is an element of real numbers. Now this is our equation, but the question is asking us for a position of the object. Well, a position is an actual point. So we can take this and look at our x components. So x is equal to 5 plus 3t, and y is 10 minus t. So that means that our position, depending on what t is, would be 5 plus 3t and 10 minus t if we write it as a coordinate. Now b is asking, what if t is equal to 3? So we can just sub that in. And we get 14, 7. For C, it's saying the time when the object is due east of 0, 0. So if you think due east, and back up here on this diagram, here's 0, 0. If we are due east, that means that our y value must still be 0. So therefore, if the y value must still be 0, and I take my y component, I have to set it equal to 0. So t is equal to 10. So that means that if we have an initial starting position at 5, 10, and then we use that the constant velocity vector to travel, which is 3, -1, we will be back at y is equal to 0 after 10 seconds. Or actually, just kidding, 10 minutes. This question is in minutes. Another type of problem we're going to look at is distance closest to a specific point. So if we look at this little diagram over here, we have a ship that's sailing from our initial point A with a constant velocity in the direction of r, and it's saying when is the ship closest to the point P? Well, the time that it's closest to the point P is when there's a perpendicular. The equation for a perpendicular is, so it says here, the ship is closest when PR is perpendicular to AR. So it kind of looks like this. So that would be where the R is, and then we would have a right angle. How we find that is when PR, because remember B is our constant velocity vector along AR. So when PR is a scalar product, which is equal to 0. So our next example, it looks like we have our origin. We have A, which is our initial position, which is -8, 3. Then we have a constant velocity vector of the direction 3, 4, and then we're being told what our speed is. So if we go back and look at our speed equation, so speed here is the square root of a, the x component squared, plus the b component squared. So let's go back to our question. Now we're being told that our speed is 10. So we have what we're given as our direction vector. So we get 9 plus 16, which is equal to the square root of 25, which is equal to 5. Well, when we do the formula, it says that our speed is 5, but the question is telling us that the speed is 10. So that means it just must be a scalar multiple. So how do we get from 5 to 10? Well, we multiply it by 2. Now we have 10. So that means that we also need to multiply our direction vector by 2. So they're kind of given a little bit more work to find that direction vector, which is equal to b. Now we can get started. So it says find the position. So we're going to start with our equations. Then we have x, y. We're beginning at our initial point of -8, 3, plus t, and we're using 6 and 8, not the 3 and 4, where t is an element of reals. Then, because we need our position, we're going to make our equation. So x is equal to -8 plus 6t, and y is 3 plus 8t. And then we'll write it as an actual point. And I guess based on the actual diagram, I should be using R here. Find the time when the ship is closest to the port, which is P at 10:02. So we have our R value, which we just found the expression for, -8 plus 6t and 3 plus 8t. And our formula says that if we want to find the closest point, we are going to multiply PR times our vector b, which is given to us as 3, 4 in the question. So let's set up PR, and it's equal to 0. That's the formula for the closest point. Well, b was given in the question, and PR we can find by subtracting. So -8 plus 6t, that's the R, the x component, minus 10. 3 plus 8t minus 2. So this is our P and this is our R. Times 3, 4 is equal to 0. So now I'm going to do the dot product. I'm going to simplify and do the dot product. So 3 times 6t minus 18 plus 4 is 1 plus 8t is equal to 0. And then when you distribute it and simplify it, you get t is equal to 1. So therefore, the ship is closest to P 1 hour after leaving the initial spot of A.